Okay, give me 1 sec. Sorry about that. Okay, where was I? Okay, so curve r equals cos 2 theta. So again, as I was saying, the trick is to look at what happens as your angle changes and see the behavior of r as theta changes. And you have to take care of those places where r might become negative, right? This changes the behavior drastically. So here, as you see, we have cos of 2 theta, so the sign changes will occur twice as fast as they would if it were just cos theta. So let's take a look at this. So I'll be sketching my curve over here. I'll have my angle theta like this, and I'll look at 2 theta, and whoops, let's try that again. Theta, 2 theta, and r equals cos 2 theta. Okay, so again, so theta will, the cosine, when its input goes from 0 to pi over 2, it goes from 1 down to 0. So here's, because theta is multiplied by 2, what I'll do is I'll start by looking at what happens from 0 to pi over 4. Okay, so then theta, 2 theta, will go from 0 to pi over 2. Okay, so when I'm sketching this, I'll be looking at what happens from 0 to pi over 4. What happens to r, it starts at 0, and it'll go down to 0. It starts at 1, sorry, it goes down to 0 when theta goes from 0 to pi over 4. So we start at 1, and as the angle increases, the radius decreases down to 0. So this should be going something like that, roughly. Okay? So when we hit theta equals pi over 4, r is now 0. Okay? So that's the first part of our curve right here. Okay, now let's look at the next part, pi over 4 to pi over 2. Okay, so now the angle theta is going over here. Okay, what happens to 2 theta? It's going from pi over 2 to pi. This is the input to the cosine function. Now, what does the cosine function do from pi over 2 to pi? It goes from 0 down to -1. Right? You have to keep in mind your trig circle. Right? Right? So as theta goes, 2 theta goes from pi over 2 to pi, the cosine goes from 0 to -1. That's the x-coordinate of the point on the circle. So now r is negative. Okay, so now it means that the angle from pi over 4 to pi over 2, I have to flip on the other side, and r will now go from 0 to +1. So it's similar to the first part of the curve, but this time it'll go this way. That's the second part. Right? So r is negative, angle is going from pi over 4 to pi over 2. All right? So if r is negative, I have to flip on the other side. It's going from 0 to 1. All right? So next piece, another quarter turn. We're going to go from pi over 2 to 3 pi over 4. So if I double that, I get pi to 3 pi over 2. This is the input to the cosine function. Well, now the angle 2 theta is going like that. So now the cosine of 2 theta will start at -1 and go back up to 0. It's still negative. Okay? So again, the angle now is going like this, but r is negative, so I go on the other side. I start then at +1 and go decrease down to 0. So this thing is just going to go back like that. That's the third part. Okay? All right. So now theta is 3 pi over 4. I look at the next quarter turn. 3 pi over 4 to pi. Double that. So this means 3 pi over 2 back to 2 pi. Sorry, that's 2 theta here. That. Okay. So the input to my cosine is over here. So the cos will go from 0 back to 1. So it's positive. So that should be simpler, right? So now the angle is in this section here. We start at 0, where we were, and we increase to 1 as the angle goes from there to there. So it's going to increase, and it's going to go to 1, like that. That's the fourth part of our curve. Maybe you see what this is going to do. Okay. Next, I continue. Fifth part, pi to 5 pi over 4. And again, I repeat, why am I looking at quarter turns? It's because 2 theta will possibly change signs at every quarter turn of, so every pi over 4. Okay, so 2 theta now goes from 2 pi to 5 pi over 2. Right, so this is back to this part again. So it'll just repeat, right? So that the pattern in the last column will just repeat. So this goes 1 back down to 0. Okay, so my angle theta is now over here, and the values of r start at 1, decrease down to 0. So as I'm moving, this thing will go back like this, which is kind of cool. Okay, so after that, it'll just repeat. I'll skip the details here. Let's do this one here, the sixth one. So my angle is going from 5 pi over 4. I better write this one. 5 pi over 4 to 6 pi over 4, which is 3 pi over 2. So now I'm looking at the angles over here. I double, and I get the behavior, which is r now goes from 0 down to -1. So now I have to flip on the other side. So I'm over here, and I go from 0 back up to 1. Like that. So this is the sixth piece. And you can probably, if you've been following this, hopefully you can probably finish it. So the seventh part will be over here, and the eighth part will be over here. Like that. So that's the curve we get in the end. Okay, it's called the four-leaved rose. Okay, I'll just okay. I'm gonna change slides. I'll just redraw it. So this is R equals cos 2 theta. This is the four-leaved rose. Okay, that's ugly, but what the hell? Okay, that's bad. Oh well. Well, that's what you get for free education. You get a crappy looking curve. Okay. A couple of last comments and then I will stop. So let's just take, I'm going to go back to the previous slide. Let's take a look at this region here. I'd like to describe this region here properly. I'll explain on tomorrow actually how this is important. If I want to describe the region which is over here, I have to check what the angles are. So my eighth, I'm just going to add this eighth part here, which should be 7 pi over 4 to 8 pi over 4, which is 2 pi. And we see here that we'd be going from 0 to 1. Okay, I skipped the seventh piece here. But you see that if you go basically from minus pi over 4 to 0, r is positive, okay? And from 0 to pi over 4, r is also positive, but coming back down. So let's just go back over here. So notice that one leaf can be described as follows. So it's r equals cos 2 theta, with theta between minus pi over 4, pi over 4. It'll give you that piece only. Is that? Okay. So in fact, you can describe the region inside, and so the region bounded by this leaf. It's one of the exercises, I think, so that's why I'm talking about it. Okay, so I want to describe the inside part here. So what is it? So the angle varies from minus pi over 4 to pi over 4. R starts at 0, goes to 1, comes back down to 0. So if you look at a segment for a certain angle theta like that, what are the possible values of r? It's anything between 0 and cos 2 theta, right? So this is the set of all polar points r theta such that theta is between minus pi over 4 and pi over 4, and r is between 0 and cos 2 theta. This describes precisely the inside of the leaf, okay? And notice that even though this is like a nasty curve, I mean, if you try to write that in rectangular coordinates, you're going to get a pretty complicated looking equation. But in fact, in polar, it's just type 1, right? So theta is between two constants, and r is between two functions of theta. So this is type 1 in polar. Okay, we'll see tomorrow what that means for us. Okay. All right, so here for the values, so R varies between 0 and close to theta. Right, so if you fix theta, you look at the segment that goes from the origin to this point, it's all points where R is between 0 and close to theta. So you're going to get, which actually looks like a leaf. But okay. All right, that's the end of 10.3. Are there any questions, comments? Man, I think everybody's here. This is a first. So no questions, comments. It's all good. Thank you, Gabriel. You're always there to make me feel better. It's yes.
For the double integrals, are we expected to remember how to integrate by parts, or is it always expected to be like quite simple integrals?
Okay. Integration by parts you should know.
Yeah.
But these are, I'm not going to say that there are not going to be any. I'm not going to tell you that. But these are special times, and okay, all right. So, yeah, all right.
But I don't know if you have access to the WebWorks, but let's say number 3 for the rectangular regions is a way to avoid using the integration by parts, or you don't?
I'd have to look at it. I don't have it close by. In the WebWorks, there might be some integration which are more intricate for sure.
Okay.
Yeah, that's possible. Yeah.
Okay. Thank you.
Marie, can R be written as between 0 and 1? Okay, so I think I understand your question. Let's take a look at this. Okay, so let's say so tell me if this is your question. If I look at the region, let's say I look at the region R theta such that theta is between this. Let's say I put this. I'm going to do two explanations here. So for the leaf, right? So take a look at this segment, take a look at this segment, take a look at this segment, right? So depending on the angle, you see that the segment doesn't always have the same length, right? So the possible values of R change depending on theta. That's what gives you this shape. So here, if I do that, what will I get? Well, I'm going to get this. So for each angle theta, R can be anything between 0 and 1. So I take this. This will go from anything between 0 and 1 is good. Here, anything between 0 and 1, 0 and 1, 0 and 1. So what am I getting? It's always just, it'll be that part of the circle of radius 1 here. That's what I would get. Okay, good, right? So yeah, so the end point of the segment depends on theta. So it extends as theta changes and it squishes back down. But if R goes from 0 to 1, then the segment is just rotating rigidly, right? Like a windshield wiper. That's all it does, like that. Okay, yeah. But that's a good question because by comparison, it helps to understand the original example. Anything else? All right. So, all right. During the quiz, I'll be around. If you have a question on, send it by Neo, and I'll be there the whole hour. And again, if you're having technical difficulties uploading, do a screenshot or something so I see that you finished before 6:30, and then you can, if you have to, you can upload it after 6:30. But just if you just upload it after 6:30, and it's late, right? So, all right. So if that's it, I'll stop the meeting and see you tomorrow. I'm not sure I'll have your quiz marked. It's really painful to mark this online stuff. We'll see. All right. See you. Quiz is at 5:30, correct? Yeah. Bye-bye.